Welcome back. We're so close to the finish line in this class, and this next topic is one that's necessary, but not really a critical topic to cover. It's necessary from a completeness perspective that to understand and to write programs that use structured data, we have to understand the syntax for it. But really, other than its relationship to pointers, as we covered in the last learning module, there's nothing here that we won't be able to handle without too much difficulty. So we're covering this concept of structured data. And let me start just briefly motivating why we care about this as a separate concept. For all of our programs so far in this class, we've been working with scenarios that have assumed that the input data kind of get can be neatly represented with just a single type. So just a single int or a single float or an array of ints or an array of floats. But most data has structure, right? Most data sources have multiple aspects. Just consider a simple C program that manipulates a student gradebook. You'll have data for the first name, data for the last name. Section could be a single character. Quiz scores could be integers. Maybe lab scores could be floating point values associated with them. And for our programs to date, what we would do if we had to implement this, we would probably make 7 different arrays. An arrays which would be two-dimensional for all the first names, an array for all the last names, an array for the sections, for quizzes, for floats, for the labs, and for each of the individual assignments that we would have here. So each student's information in that implementation would correspond to one index, right? Alan, the first student, would be index 0, and he'd be index 0 in each of those individual arrays. Ada would be index 1 in each of those individual arrays. That does work. There's nothing wrong with that approach, but I think it's pretty unwieldy as the gradebook expands, right? As you add more maybe columns to your data, the unwieldiness of your program increases pretty quickly in terms of naming variables, keeping track of our variables. In theory, one could implement a table like this as one large two-dimensional array. It's pretty complicated because you have different data types for each dimension here. You'd really just be storing kind of a raw array of bytes and then providing meaning to those individual bytes. You can do that. It's not recommended, and it'd be pretty unwieldy, I think, pretty quickly unless all of your data is of the same variable type. So when we have this concept of a struct, it's just a short for a structure. It's just a way of grouping different variables into a single type. So visually what we have is for a particular type that we are defining, we have the individual components of that type sitting back-to-back consecutive locations sequentially in memory. So we would have a structure, maybe we would call it student type, and in our student type variable, we would have some storage for that first name array, last name array, section character, quiz 1, quiz 2, lab 1, and lab 2. That would be a single variable of that type, student type. And then, of course, we could then have an array of those student types. So that would allow us then to structure that students of 0 would correspond to one of these, students of 1 would correspond to one of these, etc. Our steps for using a struct in C, our first step is we have to define that struct type. We have to give it a name and a series of data members that also have to have names associated with them. We then have to create or otherwise allocate a structure variable of that particular type. And then we have to access, when we need to update something, the data members using the so-called member access operator, the dot operator in C. Syntactically, here's what it looks like in C. We have that structure tag. Technically, as we'll see, that part is a little bit optional, but it's extremely common. So useful for declaring variables after we do that initial declaration of the structure. So this syntax is fine to follow. The keyword is struct, and we declare what our name of our structure is going to be. Then we have all the, inside our curly braces, we have all the data members that are corresponding to that structure. So this is going back to that student example that we have here. We need an array to store the first name, an array to store the last name, and then all the other data types that are part of that individual structure. These are not variables in your programs anymore, although they look like it. They are members of a structure that you then will have potentially later variables in your program of that structure type. This declares, when we do this syntax here, a variable of this type after we have our closing semicolon here, and we've declared and defined that new structure type, but we haven't actually allocated or defined any variables of this type yet. And you can do that a couple different ways, some more common than others. You can actually declare variables at the time of the actual struct definition itself. I would say this is less common because oftentimes we declare a structure type because we want to use it in all sorts of places in our program. But if you do that, technically speaking, you don't actually need the name associated with it. It still makes sense probably to have the declaration happen elsewhere. But this is valid C syntax, where we declare it at time of the struct definition. More commonly, I think you'll want to have the variable declaration separate from the type definition itself. So we define the type, and that's its own separate piece of code. And then later on in our program, at some point, we declare struct student data, student one, student two, student three. We can initialize the variables of struct types somewhat similarly to our arrays. So I would say the syntax works as one would hope for initializing our structures if we want to have that sort of compile time initialization of our structured type. So we can declare struct student data st1, and then inside of our curly braces, we can do initialization for each of the individual subcomponents of that type. Um, that's a little hard to debug sometimes. You have to remember as a programmer that first name was first, then last name was next, and then came section, then came all those elements. So you have to have a good mental map of the data structure while you're doing that initialization. So you can have bugs in your code. Someone else looking at your code doesn't necessarily understand what's happening in that structure based on that initialization. So you can also initialize by member name as well. That's a bit more wordy in terms of the amount of typing you're having to do. But here you're seeing our first instance of the use of the dot operator, our direct component initialization here. We are saying actually the first name is going to be this and the last name is going to be this. And then in that case, if you use that named initialization, the order no longer matters. It can figure out, I could have put last name before the first name, and the right locations in memory would get allocated for you. That's probably the recommended way if you want to explicitly do that kind of constant initialization of your structure types here. So that's the so-called dot operator. Just like as we are initializing, after we've created or allocated our variable, if we want to access the individual elements of our struct variable, we use that dot operator. And that's what's happening in this example here. At some point in our program, we've declared a third student. We want to initialize things like the section letter, or the quiz 1 score, the quiz 2 score, or the lab 1 or lab 2 score. We use that dot operator. So it's variable name, but variables of a structured type. We then use that dot operator to specify the component within that structure we actually want to initialize. We got to remember though that we have our strings, right? First name and last name are character arrays. We can't just set st3.first name equal to Mani or last name equal to Mina here, because they're an array. And at least on, for better or for worse in C, we can't do that direct array initialization of our variables. We have to use some function or some for loop to do that initialization. String copy will work as if first name itself was just a character array, because that's all it is. It's within this structured data, we have this character array. So that's a small caveat that the same limitations still exist within our structures. But otherwise, the data structure member is operated on, similarly or really identically to any variable of that type here. Let's just see it very quickly in action. So this code is exactly the same as what was being shown on those slides. First, we have our structure definition here of student data that just specifies the individual components we have associated with it. And we have an example of relative location initialization, where it's just going to go from element to element in order and initialize it based on the data that's provided as we've declared that variable of that type. Or there's initialization via named components. And in this case, the order is actually still the same in this example, but we could have done it in different order and it would be okay. And then finally, this third example is where we've declared the variable and we initialize it at some point in the future, where we have specified string copy in the case of our character arrays here, but otherwise just declaring via just variable initialization the individual components of that structure variable. And we get a printout as we would expect. Small caveat here, but it's something I think you'll want to have be common practice, is a separate keyword in C, the so-called type def keyword, which allows us to give an existing type a new name. That's used in a lot of the places in the header files that we're using all semester long, but we can use it in our own user programs as well. So if we thought that the word unsigned car was too wordy for our purposes, we could have in our program type def what was an unsigned character. We can also refer to it as a byte, so we can actually then use byte as a variable type here. It's similar in some sense to that preprocessor macro, that pound define, but type def is handled by the compiler versus the preprocessor, so it should be a little bit more meaningful in terms of the compiler errors we'll get when some things go wrong. It does allow us to have slightly less wordy struct declarations. So at the time of declaring our structure, we can actually say this structure we're declaring is actually going to be type def to this other name called student data. This is pretty ubiquitous, pretty common for struct types in C. So we're actually going to use it going forward just to show just in practice what that would mean. Again, this example was fine. There's nothing wrong with this code, but it's probably more common to instead type def it. And then that whole type def structure becomes a student data so that now when we want to actually use that student data structure, we don't need to use the keyword anymore. It is still a structure. It's just one that was type def to be called student data. Sometimes you'll see like, well, we'll see a reason where you may still want to have a name up here, and then we're calling it student data. We'll see an example where that becomes meaningful, but syntactically, in terms of what you're doing in your code, just a little bit more cleaner to kind of then define these as variable types without needing the struct keyword every single time. And it's the same exact thing from a functionality perspective. So we'll just do that for all of our examples going forward without really, mentioning it again. In terms of our memory view of what's happening, it's as one, I guess, would hope. Now, there's no actual guarantee that the memory contents will only be in a very specific ordering. Potentially, there'll be some padding, but generally, they're going to be adjacent to each other. So when we declare a variable of that structure type, it's going to be placed in this block of memory associated with that structure. And otherwise, though, C is going to treat your structure as any other variable type, just one that's potentially more bytes. So we can actually copy entire structs from one to another without worrying about copying each individual element. We can talk about deep copies versus shallow copies if we're using pointers. May have to be a little aware of that, but if we're not using pointers, at least we can just copy st1 to st2 and it'll work as one would hope, copying all the individual elements of st1 to st2. We can pass structure variables as function inputs and also return them as function outputs. So that's our other workaround for like one variable output from a function. It's still one variable, it's just a very large variable, so you can do a lot of work with just that one variable. We can determine how many bytes we need to allocate or how big it is using that size of operator. We also then can do structures of arrays. So those strings are themselves arrays inside the structure. That's what we mean by structure of array. But we can also have arrays of structures as well and do all the things we've already been doing with our pointers, with our either static or dynamic memory allocation with our arrays. We can do all of that with our structures themselves. Structures are really helpful for managing our data. It can get a little complicated, but for arrays, at least to start with, we first will index the array syntactically, using the square bracket operators. Then you would access the element of that structure using the dot operator. And if that element itself is itself array, then you would use the square bracket operator again. So if we, instead of declaring individual student variables, were to declare an array of students, and there's 50 students potentially in the class, syntactically, if we wanted to know for whatever reason the jth letter of student I, it would be my students of I. So that's the of an array of students. That's the individual element student of I. Then the first name component of that structure. So that's your dot operator. Usually we'd want to print out the whole thing, but if we only wanted to know the jth letter of that student of I, then you would use the bracket to grab the individual character of that. Just like when do we create functions, when do we create structures? Well, when I tell you to is a valid time to create structures. But really, when it kind of matches your application needs, right? So we like to think of in terms of solutions, at least in terms of what data types do we need, and if you foresee that there is student data processing, well, then it makes sense to have a structure that contains that student data, and you combine all those students together, and the end result is a class of students. So the next question would be, well, does it make sense to have a separate structure that corresponds to an entire class? And it can for your application, right? So what is a class if not a collection of students? And I guess there's an instructor and things like that. But it would make perfect sense, at least in my opinion, if you're doing some class level processing in your program, that you not just have an array of students that could be part of the solution. Maybe you need to have an array to store the class name. And maybe 50 is the maximum number of students, but you actually need to know what the current student count is. Structuring that together could make a lot of sense. Likewise, that's one class, and you're in a department with many classes. It may make sense to now take that class structure and then consequently have an array of classes as well as the name of the department and the number. That's the maximum number of classes. Here's the current number of classes. You call that your department data structure associated with it. So the syntax can get a little messy, but at least it's logical and consistent. So there's no tricks to it. You just have to be aware of the structure of your data and go from outer structure down to inner structure as you go from left to right. So, how would we access the third letter of the first name of the 12th student in the 5th department's 4th class? Well, that's brutal, but it's logical. So we would declare an array called my departments of department type, an array of size 100. We work outward in. So it's the 5th department, so that'd be my departments of 4. 4th class, my departments of 4 dot my classes, as it's called here, of 3. 12th students, 12th student in that class. My departments of 4 dot my classes of 3 dot my students of 11, third letter of the first name, that's first name of 2. My departments of 4 dot my classes of 3 dot my students of 11 dot first name of 2. It's all logical and consistent, and I guess I would say it's fair syntactically. You really got to keep track then of what are your structures in your program, what access do you need for those structures. Drawing it out can always help solve that problem for you. But even just having like that file open that has your structures declared separately from the code you're currently writing will make it a lot less likely you're going to make syntactical or logical errors as you are working with structures. Let's just play around with our structures a little bit more with our array of student data. Let's attempt to sort our students by last name. So I had listed this as a live programming exercise, but I just have the example that I'll show you my solution for, and I'll just kind of walk you through it here. So can we sort the students in our class by last name? Something that you can do in Canvas, but for some reason it takes like 7 seconds to sort by any given column in Canvas. Our code will show that it shouldn't be that hard. We can use our bubble sort type sorting. We also could have used our quick sort, but I think that code would be pretty ugly. Bubble sort should be okay, given we don't expect there to be 5 million students. And string comp should work for our purposes, as we've seen. String comp does this kind of lexicographical comparison. A winds up being less than B, winds up being less than C. Should work for our sorting compare purposes. Here's what this looks like in practice versus having us just start it from scratch. First, I wanted to initialize the data to something meaningful. So let's start from main and work our way down. Arguably, we should start with our actual data structure. It's just the same as it was before with type def struct of our student data that we have here. So same as it was in the previous example. We then have a certain number of students. That's our array of student data. I wanted to have some interesting names that get randomly generated. So kind of like we did with our dictionary example, have some storage to store the first and last names based on a dictionary that stores common first and common last names. So we have 2 files we're in fact reading from here. One is names F for first names. One is just names for last names. We can actually read them simultaneously because we're storing them into different arrays. So in this case, we're not worrying about exit conditions of these. We're just saying, hey, read 4,000 names and store it into an array. For first names, that covers most of them. For last names, it actually doesn't, but it's fine. We're going to read 4,000 first names, 4,000 last names using our fscanf, just like we did in our dictionary sort example from the prior learning module. Then we need to have some mechanism by which we initialize those elements of our student array here. The tricky one, I guess, would be how do we initialize our first and last names? It has to be a string copy. We have an array of first names, an array of last names, and we just pick one. Pick one randomly. We know there's num names. We know there's 4,000 elements. Do a rand mod 4,000. That gives you a location or an offset of 0 to 3999. That'll give you a valid first and valid last name. For the rest, we're just randomly generating it. So your section, if we assume it's a single capital character letter, we could do rand mod 26 to get a result of 0 to 25, and we add A to that. That'll give you A through Z as our possibilities for the section name. Likewise, for our quiz, gives us a value of, in this case, 0 to 9. That's fine. Likewise, for our labs, that's a floating point value. We can still do rand mod 100, but then if we want a floating point value, maybe we divide by 10.0, or it could have been 0 to 100 with a floating point value. That's just for purposes of showing the different data types that we have here. Then I wanted to do as we typically do for our sorts, print the array, sort the array, print the array again. Our print array function should also look pretty similar to what we've done. It tends to be pretty customized to the data structure now because we actually have to look at the different parts of the components and what we want to print out. And there's no right way to print it out, but in this case, maybe it makes sense to print out first name space last name, print out then on the separate line, section letter, and then on the last line, those elements in the grade book. Now we finally get to our sorting approach, and it is still just our bubble sort. And let me actually, before we get to bubble sort, I created a function print students. A little bit of encapsulation here. It's not strictly necessary. That allows us to print student 0, then student 1, then student 2, and then it calls the function print student. This one takes as input the entire array of students. This one takes as input a single student as input. And then that allows us just to kind of scaffold that together where print students prints a little header, then calls print student, and then print student is printing that individual student. Our bubble sort then should look pretty similar to our prior bubble sorts. The main difference is, the variable we use for that swap operation. So let's starting with that first. The nice thing about that, if you go back to our prior bubble sort, including the code that you yourself have written for your programming practice, those 3 lines should look effectively the same. Only difference is the data type here. Is this structured data type versus an int or a float or some other just scalar data type here? But in C, our structures can operate via this copy mechanism, so I can just kind of swap values using a temp structure to hold the temporary value that's about to get swapped out. If there were pointers within that array, the pointers themselves would get properly copied over. The data that they're pointing to would not get copied over, so we have to be a little bit careful when doing that. But for purposes of this and for a lot of our other examples, this so-called shallow copy is sufficient for our purposes. And then the only other difference, our for loops are also exactly how we've been doing bubble sort all semester. The only difference is that comparison function and that string comp function, which checks one string against the other, checks if they're equal, and if they're not equal, which character came first that was different and which one was greater than the other character that came first. That actually works exactly as we would hope. We compare J to J plus 1, and B is going to be greater than A, and C is going to be greater than B. And the end result is an array of students that before sort, they're just randomly generated students with our last names as we have here. It looks kind of sorted, but it's not. There's A, B, C, and then it goes back to A, B, C. There's a lot more last names than first names, so that's why it looks like they're all pretty low. And then after the sort, you can see our last names are in fact in reasonable order here from A through C at the end. So as we've seen, sorting is a pretty powerful tool, whether we're using qsort or whether we're writing our own bubble sort. Structures are kind of just a small additional abstraction on top of the existing variable kind of bookkeeping we've been having to do all semester. I would argue, while there is new operators we have to learn, and there's one more we're going to cover in the next video we have here, it actually makes your code a little bit cleaner and a little bit easier to write. We could have written that same sort students code without using structures at all. I feel like that code would have been a lot harder to read, to write, to understand. It would certainly have been more lines of code. But by declaring this structure, we kind of encapsulate our data very nicely. And then the sort operation is almost a copy paste from our prior sorting operations. And it's nice and clean. And it does what one would hope the language allows us to do for dealing with those structured data types as kind of a built-in variable for all of the operations you expect it to have. We're going to cover pointers and structures, which is a critical topic that I would want you to understand well before jumping into the last set of assignments we have here. I'll see you in the next video.